Hello, 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 and welcome to Shiksha Dakasa. Today we're going to learn how to transform sinusoidal functions. So today we're going to learn about the function f of x equals sine x with all of these other letters or these other variables in between. These are called parameters because these are actually representing values that we can control, and they in turn would affect the graph of f of x equals sine x. And throughout this lesson, you're going to determine through an investigation what are the roles of those parameters on this function. And you're going to be able to describe those roles in terms of transformations of the graph f of x equals sine x with angles and degrees. To start off, I want you to think back to the previous lesson where we talked about each of these diagrams and we figured out how do we calculate the angle that has been rotated so far, and then how do we find the coordinate of the point that is rotating around the edge? How do we find the y coordinate? Go ahead and pause the video here and see if you can figure that out for this first row. Well, if you have not already, hopefully you realize that if we're measuring the time in seconds, this wheel has a radius of 1 and the rotation speed is 1 degree per second, while the y coordinate, which is sort of the height of this point above the x-axis, can be found by the function sine x. And when I say sine x, I mean because the angle that has been rotated, because it's 1 degree per second, the angle of rotation is the same as the number of seconds. And if we want to find the height of a point above the center of the circle, that's just the function sine x. From here, why don't you go ahead and try to see if you can figure out the second row. Notice that this circle is the same as the first one, except its radius is doubled. Well, the angle of rotation doesn't actually change. In fact, if you compare these two, you might notice that both of the triangles are sort of changing at the exact same rate. So the angle of rotation is still dependent on the time. It's 1 degree per second, so it's still just 1 times x, or just x. But the y coordinate is a little bit harder to figure out. If we were to try and make that right triangle, we might say, okay, the opposite side is still the y coordinate, but now the hypotenuse is 2. And if we isolate y, we'll find out that the y coordinate can be found by taking 2 times sine of x. This height is always going to be double the height from our original circle. So go ahead and take a look at this third row. Now the radius is back down to 1. The rotation speed has increased, spinning a lot faster. This is 3 degrees every second. The center is still at 0 on the x-axis, and it still starts with a rotation of 0 degrees, so it still starts over here on the right. How do we find the angle of rotation? And how do we find the y coordinate? Pause the video here and see if you can figure it out. Well, hopefully you saw that, okay, well, if it's 3 degrees per second, the angle will be 3 degrees times the number of seconds, which is x. That's just 3x. And the y coordinate can be found by taking the sine of this number, so sine of 3x. What if the circle was back down to radius of 1, back to spinning at the exact same speed as it was here, but now the center has been moved up by 2 units. The height of the center is now 2. It still starts with with a rotation of 0 degrees, so it still starts right here. How do we find the angle of rotation? Well, very similar to these two rows, it still only rotates 1 degree per second, so that's still just x. But to find the y coordinate, not only do we have to find the height of this triangle, but now we have to add the height of the center, right? Because sine x tells us the height of a point above the center of a circle. But that center is already 2 units above the x-axis. So the y coordinate will actually be sine x plus 2. Finally, see if you can figure out this last row to see what the y coordinate would be if the point doesn't start on the right like it does in each of these, but it actually starts at the top with an initial starting rotation of 90 degrees. Well, to find the angle of rotation here, it's not based on the number, it's not exactly the same as the number of seconds. We have to take the number of seconds and we have to add the amount that it started with, which is 90 degrees. So it's actually going to be x plus 90. And to find the y-coordinate, well, just like these circles, all we have to do is do sine of whatever the angle of rotation is. So sine of x plus 90. Now, taking a look at all of these, what I want you to try to do now is graph each of these expressions one at a time and see, what do you notice? Well, once you graph them, you should see some graphs that look sort of like this, and this, and this, and this, and this. What do you notice about each of these graphs? Let's go through them one by one. First up, we've got this graph here, and this is exactly the graph f of x equals sine x. This is our normal graph. It's got an amplitude of 1, a period of 360 degrees. Its midline is y equals 0, and it starts on the midline, and it starts by increasing at 0, 0. Well, this function, 2 times sine x, looks like its amplitude has increased. In other words, this function looks like it looks like we grabbed the purple function at the top and the bottom, and we pulled it apart. It's almost like we stretched it vertically in the vertical direction. Horizontally, we notice it has not changed, right? It still ends after, or one period is still exactly 360 degrees. But if we look at just the next row, in this case, when we multiply x by 3 before we put it into the sine function, it looks like that does something as well to the function. It used to be looking like this, but now looks like it's been horizontally compressed. It's like someone pressed on it from the right and from the left side and squeezed it, so its period is no longer 360. It's actually 1/3 of what it used to be. Now it's only 120 degrees. When we look at the circle that had been moved up by 2, and we look at the equation that, or the graph that sine x plus 2 creates, it looks like this entire sine wave is congruent to this one. In other words, it's exactly the same shape, but it's just been translated or shifted up every single point. Looks like it was moved up by exactly 2 units. And finally, if we were to add a certain number of degrees inside of the brackets before evaluating the sine function, we see that, oh, this function has actually been shifted to the left. It used to start right here. Now it's here at -90, but the shape is still identical. So in that investigation, hopefully you saw that for the function f of x equals a times sine of k times x minus d, double bracket close, plus c, this is the fully transformed sine function. And we can transform this function by doing all sorts of stuff to it. The first thing is after we evaluate the function sine, by multiplying it by a number, we're going to call that number a. Changing this value of a, it usually starts at 1, but changing it causes the function to become vertically stretched or compressed. And if we reduce it so much that it's negative, it even becomes reflected. So now it's upside down, just like we see here. This, of course, changes the amplitude, right? We can get bigger or smaller. And by doing that, it changes the maximum and minimum, which are dependent on the amplitude. They're the distance of the points from the midline. That's what we call the amplitude. So if the amplitude changes, well, the bottom and the top values aren't going to be the same either. And because the range is dependent on the maximum and the minimum, that will also change whenever you change the value of a. But notice what does not change. The period is still 360 degrees. The midline is still at y equals 0, and therefore the domain has not changed at all. When we change the value k, and by that I mean, what if we multiply x by a number before we plug that number into sine? Well, changing that value causes the function to become horizontally stretched or compressed. But it sort of works backwards from a, and this is something that a lot of students will make a mistake on. Whenever the value of k is big, that actually compresses the function, as we see here. And when it's small, but when it's between -1 and 1, that stretches the function. as we might see right here. And of course, very similar to A, this is the only way where they're sort of similar, is that when the k value is negative, that reflects the function. Now, because the k value stretches it horizontally, notice that the period is changing. And the period will change to 360 divided by whatever the absolute value of k is. So even if k is a negative number, we actually just take that to be a positive number. That's what the absolute value means. When we horizontally stretch or compress k, though, another really confusing thing about it is that the way we describe it, because when it's big, it's actually being compressed. We say it is compressed by a factor of whatever the reciprocal of that number is. So if k was 2, that would be a compression by a factor of the reciprocal of 2, which is 1 over 2. The changing the value of k, though, does not actually change the amplitude, which remains at 1 here. It doesn't change the maximum or the minimum or even the midline. It doesn't change the range because the maximum and minimum have stayed the same. And it doesn't even change the domain because the domain is every real number. However, it might change the domain of one period if we were looking at just one period, but that's about it. Now, if we were to add or subtract a number before we multiplied by k, well, that value we call the d value. It's also one that is a little bit confusing. Now, when the d value is increasing, when it's positive, the function seems to move to the right. And when it's negative, the function moves to the left. And that kind of makes sense, right? If we increase a number, we're moving right on the number line, and if we're decreasing it, we're moving left. The confusing part happens when we recognize that the expression x minus d is x minus d, not plus. So if d is 4, this would look like x minus 4. And that can get a little bit confusing for some students as well. Notice that d doesn't really change a whole lot of things. It doesn't change the amplitude, the period, the midline, the maximum, the minimum, the domain, the range. All it does is change where the starting point of the sine wave actually is. Finally, we have the value c. So when we add or subtract a number after we have multiplied by a, so after we've done the sign of whatever the input is, and then multiplied it by another number, if we add or subtract a number now, that would cause all of these points to translate up or down. If the value of c is positive, the function will translate up. And if it's negative, it will translate down. And this, of course, will change where the midline is. And then that's the most important one. It does not change the amplitude, but it still changes the maximum or minimum just because that is a function of a distance from the midline. It also does not change the period because it doesn't, move this or stretch this function horizontally or compress it. And it also doesn't change the domain. In this example, we might say, okay, well, if I know what a, k, c, and d do, what is the equation of a sinusoidal function that has gone through all of these transformations? Well, the first thing to always write down is what does the fully transformed sine function look like? And that's the template that I'm going to start with. Now I'm going to go through each of these and see what I can understand them to actually mean in terms of the equation. For example, if it's been vertically reflected, that means I know that the a value has got to be negative. And if it's compressed by a factor of 1 over 2, well, then I know that this was multiplied by 0.5, 1 divided by 2. And because I know that the a value is negative, a must be negative 1 over 2 or negative 0.5. If this function was horizontally reflected, well, that would actually change the k value and make it negative. That means that the k value must have been negative, otherwise it would not be reflected horizontally. And this is where this is kind of a tricky one right here. If a function has been horizontally compressed, that means that the k value is actually a bigger number, bigger than 1 or lower than negative 1. By a factor of 1 over 2, well, that tells me that I have to take the reciprocal of this, and the reciprocal of 1 over 2 is 2 over 1. And because I know it's negative, k has to be negative 2 over 1, which is just negative 2. If the function was shifted 3.9 units to the right, shifting to the right means d is a positive number, and therefore d would be positive 3.9. Of course, in my equation, it'll actually look like x minus 3.9, but the value of d is still positive. Finally, we've got the value c at the end here, and because this was shifted down, I know that c has to be a negative number. In this case, it is negative 4. So now that I know a, k, c, and d, I can actually just put those numbers right in their correct spots. So a is negative 0.5, k is negative 2, d is positive 3.9, but of course this is x minus 3.9, and c is negative 4, and that just goes at the end there. In this example, you can, and I'll ask you to actually pause the video here and see if you can describe all of the transformations that have been applied to transform sine x into this massive function. Well, hopefully you know that the best starting point here is just to write down the transformed functions template. And now we recognize where that each of these values, have a very specific number assigned to them. For example, the value of a here is 3, k is negative 0.5, and so on. And because a is 3, that means that there has been a vertical stretch by a factor of 3. It's not negative, so there was no reflection. And because k was negative 0.5, because it's 0.5, that's a small number, so that means the function was horizontally stretched. And it was done that was done by a factor of the reciprocal. So the reciprocal of 0.5 is 1 over 0.5. And if you actually divide these, you'll get 2. Now, because k is a negative number, because k is less than 0, there has also been a horizontal reflection. Next up, we have D. In this case, although we see x plus 180 degrees, the value of D is not positive. It's actually negative because this maybe used to be x minus negative 180. And when you subtract a negative, you end up with a positive. So x plus 180 just means that D is negative 180, which means the function was shifted 180 degrees to the left. And finally, our value of c is 5, and that means that this function was shifted 5 units up. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.